now switch tack a little bit and move into a science session and to really look at FH and beyond, a scientific take on familial hyperlipidemias. And I would like to invite once again Professor Bourbon Mafalda to take the floor, and then afterwards we'll be hearing from Kanika Diarmiayat from the EAS FH Studies collaboration based at Imperial College London. So let's kick off with you, Mafalda, and if you join afterwards, that would be fantastic.
Thank you, Nicola. I have to take my phone because I talk too much and Nicola is going to shut me up in 15 minutes. So I will try to be, but I would like not to speak too fast so you can understand by my slides and we can discuss afterwards. So FH, the broader meaning of FH can be familial hyperlipidemia. And in FH Europe, you have different familial hyperlipidemia that we advocate for. So we are going to talk more about FH, but also I'll have some slides about hyper-Lp(a) and FCS. So where do I have to point? It's not doing it. I'm losing some minutes that I need. So the first slide that I have is a table with the different familial hyperlipidemia. I'm sure that most of you know about FH. It's probably the disorder that you know better because it's the most common. And even if we don't talk enough about FH, we start hearing about FH everywhere. Okay, here's the table. So you know that there's two forms of FH, heterozygous, homozygous FH. And you know that now the prevalence of this disorder is much higher than we thought. I started on FH in '97 with my master's degree in the Hammersmith Hospital in London. And from that on, FH has been my life, apart my family and FH, half-half. Yes, my husband is a bit jealous of FH, I must say. But I have dedicated my life to research on FH and bring everything I learned in the UK to Portugal and set up the Portuguese FH study here in Portugal. And with FH, all the other dyslipidemia come up as well, because people were asking me, like, can you study other dyslipidemia? I have a patient with suspected FCS, for example, or hypobeta-lipoproteinemia. So different dyslipidemias. And here you can see that familial hypercholesterolemia is the most common, but then we have autosomal recessive hypercholesterolemia and cytosideremia, that there are two lipid disorders that they mimic homozygous FH, so they have very similar phenotype, but they are much rare. Then you have hyper-Lp(a), that it can mimic FH as well, and I'm going to show you a slide about that in Portugal. And then FCS, as Jill has spoken here, it's very rare, but it's very conditioning for your life, and you presented different symptoms from FH. So I will speak more about FH, like I said. So FH, the clinical presentation, probably you all know, but I think it's good to remind, because everyone knows what's FH, but no one is diagnosing FH, and that's real the problem. So FH is really easy to diagnose. So if someone comes to a clinician, we do blood tests all the time. In Portugal, we start doing blood tests at 20. Usually everyone at 20 does one, and then at 30 and 40. So you have many times that you can find FH in these patients. But we're not finding the patients that we should. So if you have a high LDL and you have a family history of high LDL, that makes a diagnosis of FH. Then, of course, you can go into genetic testing, and I will talk about that later. But you can also have a family history of heart diseases, and that should be, at least on those cases, you should be tested for FH. And we know now that the presence of tandem xanthomas that was very, very characteristic of FH, we cannot find anymore in FH patients because of all the statins that have been introduced in the 80s. But we know that FH is the most common monogenic dyslipidemia and the most common that this confers a high cardiovascular risk and is preventable. So we really need to do something. We have different clinical criteria for FH, so that's not missing. We have the Simon Broom, we have the Dutch, the World Heart Organization, we have criteria for children in the UK registry. So we have all the tools to be identifying these patients. And here is just a cartoon that I did actually for a prize that I won with my team to explain what was FH. And here you can see that when a baby is born, even in the uterus, the cholesterol starts accumulating and then starts accumulating through life. And then when you reach 30 or 50 years old, if you're not treated, your artery is going to be blocked and you're going to have a heart disease, you're going to have a heart attack. And this happened when I started at the Hammersmith in 96, 97. 80% of the patients would have early myocardial infarction. Now we could go down to 30% all over the world, probably in all cohorts, we just have 30% of people with myocardial infarction because the statins came in the 80s and then so many other life-changing therapies showed up. So we are still with 30%. We should be at the 0% with all we know and all we have. But we also know that when we have all these treatments, and if we identify early, you can even prevent the plaque growth. So it's not only to reduce, you can prevent. So this is why it's so important to identify these patients. On the genetic side, that's where I work, we know exactly which are the genes that we have to study. We know that 90% of the cases have variants in the LDL receptor gene, and only 5 to 10 in the ApoB gene, and only 1 to 3 in PCSK9 gene. But in the other side, we know so much about genetics now and have so many good equipments and techniques to study all these disorders that we just find a lot of variants. And that is kind of a gap in FH diagnosis because we have so many knowledge about FH and so many knowledge about these genes and the variants, but there are so many variants. So I don't know if you have an idea, but we have 2,800 variants in these 3 genes. And half of them, they are variants of unknown significance. So we don't know if they cause FH or not. We need lots of research here. And what means that a variant of unknown significance? These variants, they cannot confirm the diagnosis of FH, so they are not clinical actionable. So we need to do more research and collect more data worldwide to have more information about these variants, and we can confirm FH in more cases that we have under study. This is just for you to see that that's the number of variants we have, like 2,300 in the LDL receptor, and then 300, 200 in the other genes. But this is a lot of variants that we need to study and understand to then give you a diagnosis. And the genetic diagnosis is really, really important. Of course, I know that in some countries you don't have it, and so you have to go into the clinical diagnosis at least. But if you have genetic diagnosis, you should do it because you cannot distinguish who has FH from an LDL value. You can see here in blue and red, people with FH and without FH, and the LDL values are exactly the same. So only the genetic diagnosis can tell you what if you have FH or another lipid disorder that needs to be further investigated. And the genetic diagnosis can give you information about many things, about the treatments, and so it gives you many more information than just the variant. So we reach a point that we know that due to lifelong exposure to high LDL, these patients develop premature heart diseases, and we know the genetic causes, and we know that there's several treatments out there that can reduce the risk of these patients. So we just need to identify them. This is the huge gap that we have, and as early as possible. I'm going to try here something that probably looks complicated to you, but I would like to explain you the LDL receptor cycle. Probably you never heard, you heard about it, but you never saw it like, and I will try to explain. So this is, imagine this is a liver cell. This square is a liver cell. So it is in the liver that the lipid metabolism happens. The majority of LDL clearance happens in the liver. So let's go through here. So you have three genes, LDL receptor, ApoB, and PCSK9. These three genes, they codify for proteins. And that's what we going to speak about here. So we have the PCSK9 and the LDL receptor proteins. They are made in the liver, and then they are secreted outside. The ApoB is also made in the liver, and it's secreted outside with the LDL particles. So is this pink snake around LDL is the ApoB. So what happens? You have this blue, that's the LDL receptors, and their job is to capture this molecule of LDL with the ApoB. And when they do a good binding, and some of the PCSK9 is like a controller of all this cycle. So it binds in some places, it doesn't bind in other receptors. So then this is internalized, and when you have it in the side of the cell, it goes through different steps. And here in endosome, it's like dissociated. So the receptor goes up to the surface again to capture more particles. And the LDL and the ApoB goes to metabolic use. You need the amino acids for other functions of the body. So this is happening. One receptor can do this 10 times in 1 hour, and then another one is produced. If you have FH, you can have a variant that affects the binding, affects the internalization, affects the recycling, affects the production. And if you know exactly the mutation you have, you can personalized treatment, because you have different treatments that are better for each part of the cycle. And we are not completely there, but we will be there where a place where we have a personalized treatment for FH patients. So instead of taking 3 drugs, maybe you just need to take 1 if you have, like, for example, a recycling defect. So this is the way forward. We are working on this to improve treatment and improve your quality of life with personalized medicine. So just a few slides about the Portuguese FH study. So starting in 1999 with my PhD, I have a huge network in Portugal, 144 clinicians. But what happens? They only send 1 or 2 patients per year. They're not, I don't know where the patients are. They don't know where the patients are, and this must be, something must be done. Another good thing about the Portuguese FH study is that we have plenty of pediatricians. We have 50 pediatricians. 40% of our indexed cases are pediatric patients. So we are doing well on early identification of patients. But we are not doing well on FH identification. This is Portugal, 5 continental regions and 2 islands. And look at the percentage we have found of FH patients. And you were looking at the higher prevalence, or the 1 in 500 prevalence, so the old prevalence, because I have no means of knowing that if I have a higher prevalence in Portugal. We don't have enough cases to say that our prevalence is 1 in 300, as many studies say. And here are our results. So we have 41% with heterozygous FH, the ones that we studied with clinical diagnosis of FH. 41% have heterozygous FH, 1% have a homozygous FH, and 1% have other lipid disorders. So they were cataloged as FH, and they have completely different disorders. The one I talked to you about, cytosinemia, or we don't have ARH in Portugal, but we have other lipid disorders. Then in the ones that they are negative for the 3 genes, we have found that 20% of all these patients with clinical diagnosis of FH, they have hyper-Lp(a). Then we have some patients with high polygenic risk score. This means that they don't only have 1 variant that is the cause of disorder. They have many variants that have small effects, but that reaches the cholesterol to very high levels as well. And then we have 20% without unknown causes, and we don't know why these patients have high LDL. So we still have a lot to do on the research side. But we can now draw this figure, and this is very good because some years ago, we could only say which ones have heterozygous FH. So now we can add a bit more explanation to the FH phenotype. So just 2 slides now about hyper Lp(a). We had a seminar just 2 weeks ago, so I'm sure all of you know, but I just want to remind you that the level. So it's considered to have high hyper Lp(a) if you have more than 50 milligrams of deciliter or the 125 nanomoles per liter. We should be looking at the nanomoles per liter because it's a more accurate measurement in nanomoles per liter. And these we know that are associated with a higher cardiovascular risk. And we know that if you have very high Lp(a), so 180 milligrams per deciliter or 430 nanomoles per liter, you have associated with a lifetime cardiovascular risk similar to FH. So this is having these values of Lp(a) is the same as having FH on the side of the cardiovascular risk. As Gipe just said today, you just need to measure once in your life. So we do so many other diagnostic tests that we could do Lp(a) to everyone as well. And this was very surprising to find that in these last guidelines, that Lp(a) is associated to aortic valve stenosis. And this was something that we didn't know before these last studies. So this is quite important. And it's important to think that the Lp(a), hyper Lp(a), mimics FH phenotype. So you need to look into the patients that have a clinical diagnosis of FH to see if they have FH or hyper Lp(a), or maybe both, because we know there are some people out there with both. The genetic diagnosis, it's not done for the diagnosis purposes. We are still doing lots of research, and because it's a new condition, we have to, but we know the gene, and so it's going to be fast until we have something to do on the genetic side. But biochemical test is more than enough to identify hyperlipidemia. FCS. So FCS, like the main, as Jill said, the main clinical manifestation is very high triglycerides. Oh, very short, okay. Because you were looking at, no, this is more or less, yeah. And you have recurrent pancreatitis, but we know the genes as well. So the majority of people have LPL or ApoC2, and then we have 3 genes that were discovered in the last years. And probably, as Jill has said, maybe the prevalence will increase because now we have more genes and probably more patients with variants in these genes. So just my final slide is a very, very clean message. So we have lots of ways of doing a genetic diagnosis. We have lots of treatments. Pharma companies that are doing a wonderful job in finding more treatments for all these conditions. But we need to improve clinical diagnosis. That's exactly our gap. And that's what we are doing here today with the FH pediatric screening subject. And this is what is more important. And just to show you that guidelines are not enough. We have a guideline in Portugal since 2013 and says that every child has to do a lipid profile, and this is not done by the clinicians. So we need to do more than guidelines. As a community and all of us together, we need to find a strategy that works, because only guidelines, they don't work. And this was all I wanted to say to you today.
Great. Thank you to Magda and FH Europe for this kind invitation. And on behalf of all the investigators from the FHSC registry, I'll be presenting findings on over 11,200 children and adolescents with heterozygous familial hypercholesterolemia from 48 countries. So Professor Bourbon just mentioned about the pathophysiology of FH, and I would like to approach it from the perspective of population health. So FH is a global disease and affects 1 in 311 individuals. So this means that there are potentially more than 25 million individuals with FH worldwide right now. But despite FH being a very common disease, globally, less than 10% have been identified to date. So the aim of FH care is for early detection and early treatment, and this is visualized nicely in this figure, where we can see in the red, where we can see in the red line, which is individuals with FH, that they're exposed to elevated levels of LDL-C from birth. So it makes it imperative to identify early so that we can treat early, not just with medications, but as Indy and Danique mentioned earlier, that you can promote good lifestyle behaviors, so we can effectively course correct and ensure the individuals with FH have LDL-C levels that match that of those without FH, so the general population, which is the green line. Sorry, I don't think that's very clear in this. So in order to find individuals, typically a healthcare system around the world will look at performing screening followed by diagnosis. And again, I just want to mention that with FH being a genetic condition, there is a 50% chance of that gene being passed on to the child. So in order to find individuals with FH, healthcare systems will typically have to undertake some form of screening. And this is so that we can stratify individuals that are going to be suspicious of having FH. And two examples that I'm going to talk about here, universal screening and cascade. So universal screening is typically where we'd identify or screen all individuals within a defined age group. So this could be, for example, all children aged within 1 to 9 years of age. And the individuals that would be found with FH would be known as index cases. Cascade testing, on the other hand, are whereby children are tested because their parents have been found first. So once we found children with, that we think are suspicious of having FH, how are they diagnosed? Well, they can be either through established clinical criteria and or genetic testing. And some examples are listed in the red box. So as mentioned by Professor Bourbon earlier, Simon Broom, MedPed, DLCN, etc. But we have to note that they were primarily derived for use on adults. So we're not exactly sure how they perform on children, even though some have been modified. Now, genetic testing, on the other hand, is a gold standard methodology, but unfortunately, it's not available or accessible in every region of the world. So to address the gaps around screening, so finding individuals and then diagnosing them, diagnosing individuals with FH, the FHSC network and registry was established in 2015 and currently has 68 countries participating in this initiative, as highlighted by the darker gray of the world map. This is a busy slide, but so essentially our first publication from the registry was based on the adults. And what we found was the adults in our registry were diagnosed in their mid-40s, 44 years to be precise. And highlighted in the red box, we can see that of these adults, which were over 40,000, only 2% were diagnosed when they were children. So this means that there was 40 plus years of missed opportunity to identify and change their lives. And when we looked further into these adults, we saw that actually 1 in 6 adults in the registry already had cardiovascular disease when they were diagnosed. So if we don't identify early, then we can't treat early and therefore prevent cardiovascular disease. So the next step in our registry was to undertake analysis on the children within the registry, specifically to understand how are children currently being screened, i.e. found, and how are they being diagnosed, so that we can potentially find solutions to the current gaps that exist. So in our registry, we have over 63,000 individuals, and from the 48 countries, as highlighted in the far right corner, 11,231 children were available for analysis. Now, when we group all the 48 countries, we can see that all regions of the world are represented in our registry, and notably, over 90% come from Europe. So we still have to do considerable work in these other regions. I mentioned earlier about index cases and non-index cases, and we can see on the bar graph on the right-hand side that in our registry, around 67% of the children were identified as non-index cases, which means that they underwent cascade screening, most likely due to their parent being found first, probably most likely due to having a cardiovascular event, which triggered that parent being tested for FH. Now, of course, cascade screening does have its merits, but as healthcare systems, we've not been that great in actively finding adults to find children. So we do need to move towards more universal screening and focusing on children. Again, this is a busy slide, but from the registry, we can see that the typical characteristics that the children presented with. So on average, they were 9 years of age, and the typical diagnostic features of FH, so corneal arcus and xanthoma, are virtually absent, as is coronary artery disease. So this means in childhood, if we're going to look for FH, we're going to be reliant on LDL-C levels and/or genetics. And we can see in the bottom graph just how much higher the LDL-C levels are in individual or children with FH compared to the non-FH children. Once the children were screened for FH, how were they diagnosed? Well, again, different criteria have been used based on the countries that they're from, but overall, over 70% were diagnosed by genetic testing. Now, of course, it's been mentioned that genetic testing is not available or accessible in every region of the world. So this means we're going to be reliant on clinical criteria to guide diagnosis. So in our registry, we wanted to assess how do the clinical criteria perform in in determining FH in children. And we can see that the criteria that have not been adapted to children, the LDL-C levels measured are much higher than the gold standard, which is the genetic testing at the bottom. Whereas the criteria that have been adapted or modified to children, the LDL-C levels are somewhat comparable to genetic testing. So essentially what this means is that if we don't modify criteria for clinical criteria for children, it means that we're only going to be identifying those with very high LDL-C levels. So children that have FH but have low levels of LDL-C levels will be missed. So in order to ensure that children of all LDL-C levels are identified with FH, we then created percentile curves by gender. So on the bottom, the x-axis are ages from 0 to 17.9 years. And then on the y-axis is the LDL-C. And again, this is quite busy, but essentially the dark black line is the 50th percentile. So in the registry, what it means is that around 50% of children have LDL-C above that dark black line, and 50% have LDL-C below that dark line. So essentially, it means that there are children going to be having different variations in LDL-C levels, but they do have FH. But notably, we can see just how much higher the LDL-C levels are from 0 to 3, 4 years of age in both boys and girls compared to the other ages. And that's factored in especially more when you consider the non-FH children LDL-C level, which is the horizontal blue line. So in childhood, this means that we can use LDL-C levels to determine FH, especially when we can see that there is a clear difference in those LDL-C levels between children having FH and not having FH. So to summarize, currently, we're mostly practicing cascade screening, and if we want to identify children more so that we can identify early and treat early, we do need to move towards universal screening. We cannot rely on the traditional forms of diagnostic criteria that rely on physical signs to determine a diagnosis. And if we're going to be using clinical criteria, they need to be modified somewhat for children so that we don't miss any children. And I would like to end with this. 1 child is born with FH every minute. So that means that currently there are 6.4 million children with FH right now. So we need to undertake screening in childhood. with either LDLC and ideally genetic testing so that we can correctly identify these children and help prevent a manifestation of cardiovascular disease in this group. Thank you for listening.
Thank you so much, Professor Mafalda, and thank you so much, Kanika. I hope that what those presentations have brought to you is putting into wider context what we're trying to achieve. So we have a community of people living with different conditions. We have stories of what it could be like and should be like when the condition is being identified early. And unfortunately, what happens when they are not. And we have now knowledge and evidence to help us go back to our countries and advocate for what is right for our communities. There have been some references to different papers and data. Some of it might have been a little bit complicated. Some other things might have been a little bit easier to understand. But we have prepared for you those beautiful folders with those amazing hearts on it. If you grab it, and I'm just going to take one. We want to make sure that whatever you get here serves the purpose. It's not just a nice to have. We want you to be equipped. So in the folder, you have with you the agenda, very important. And I know that Nicola is going to be very upset because I am already taking some time that was not scheduled. We have those important papers, publications, scientific data, which says why we need to test for Lp(a), like JP was saying earlier, the screening that supports what Kanika was just saying right now, the latest consensus paper. Again, ladies and gentlemen, part of being an ambassador and a leader of a community requires of us to be up to date with the latest developments, to translate the science into the languages of politicians and other people. That's our job. And there has not been a better opportunity in a meeting like this when you have the experts, when you have Professor Mafalda, when you have Kanika, when you have the patients and sponsors and other stakeholders to ask questions. Use this opportunity. And in the meantime, please go on social media and spread the word because we really need to make sure that everybody knows about it. Thank you.